We have a circle, radius r, axial ray, axial direction through the center, an incoming ray parallel to the axial ray at a distance delta x from the axial ray, where we assume delta x is significantly less than r. The angle of incidence we'll call theta sub I, and we'll note then that theta sub I is approximately equal, and the approximation works well as long as delta x is less than r. It's approximately, equal to x divided by r, where this is, we note, in radians. So we want to find the angle of refraction, assuming we have some index of refraction in here. So index of refraction, we're going to use the symbol n for the index of refraction. So what's going to happen is the light is going to, if n is greater than the index out here, we'll assume this is air, and this is water in our problem, but we'll just use n here. Okay, so if this is n, then it's going to be greater than the index in air, and the ray is going to be deflected closer to the normal direction being the radial direction. So now we have theta sub r. And the ray is going to hit the back of the lens at some point. At that point, we draw the radial line, and that's going to be the normal. So we're going to have another angle of incidence, which I'll call theta sub I prime. Okay, and that'll be this angle here. Now, we want to find this angle, and we also want to find the position at which the ray hits the back of the lens. And to do that, we're going to have to figure out this angle theta r and do a little bit of trigonometry with this triangle. So actually, we won't need the triangle to find this distance here, the proximity of this point to the axis. But we're going to have to analyze this triangle to figure out what the angle theta sub I is. So let's proceed to just write out the expression for theta sub r. We know that sine of theta sub r over sine of theta sub I is equal to what? It's going to be the index of refraction of the air, which we take to be 1. It's actually a little greater than 1, but we don't worry about that. It's so close to 1, over theta sub r, which is n. So that sine theta sub r equals sine of theta sub I over n. Now we go to the small angle approximation. The sine of theta sub r for a small angle is just theta sub r. Again, considering the angles to be in radians. And sine of theta sub I is just theta sub I. So we have theta sub r is approximately equal, and this is a very good approximation, to theta sub I divided by n. Now, of course, theta sub I is approximately equal to x over r. So that theta sub r is approximately equal to x over n times r. Now, we have the expression for the angle theta sub r. How much closer does the ray get to the axial ray over this distance? Well, if delta x is a lot less than r, the distance the ray has to travel from here to here is very close to 2r, simply because if x is close to r, this point is very nearly at distance r from the center, as is this point even more so. Excuse me. At the risk of cluttering up the picture, I'm going to draw this ray, okay, as it would be, as the first ray would be if it continued undeflected. And then I'm going to join that here to make a right triangle. And this angle here is obviously theta sub I minus theta sub R. So that's our angle here. So this side is going to be what? It's going to be approximately 2R times the sine of theta sub I minus theta sub R. But theta sub I and theta sub R are small angles, so that's approximately, well, that's going to be equal to 2 pi times theta sub I minus theta sub R. So the distance here is delta x minus this. Now these expressions can stand a little bit of simplification. So let's proceed with that for a minute. Substituting x over r for theta sub I and x over n times r for theta sub r, we get 2r times delta x, not x, and this should have been delta x down here as well. So it's delta x over r minus delta x over nr. But we can factor out the 1 over r, and that's going to divide the r here, giving us 2. Actually, we can, yeah, got a little ahead of myself there. Let me pause and fix that. Okay, we factor out the delta x as well, so we get 2 delta x times 1 over r. No, we don't have 1 over r. I'm going to fix that as well. Put it right here in front of your eyes. Didn't write down the x. I'm going to pause and fix that. Okay, we factored out the actually a delta x over r. The r divides the r. We get the delta x out in front. This term just becomes 1, and this term becomes 1 over n. So for water, n is about 1.33, which is about 1 1/3, meaning this is 1 divided by 1 1/3, 1 divided by 4/3, which would be 3/4. 1 minus 3/4 is 0.25, well, 1/4, 0.25, and 2 delta x times 1/4 is going to be 1/2 delta x. So we'll write it that way. 1/2 delta x for n equals 1.33. Okay, rather than writing and blocking the video, I just chose to write out the details here. This is simply a picture of what we have here. This picture is a little too cluttered, so we've gone here and resketched it. Now, I'll note that this angle here is the same as this angle here, since we have a radial line that cuts 2 parallel lines. Okay, so just corresponding angles in a transversal. Okay, so we have theta sub I here. We have distance 2 delta x times 1 minus 1 over n here. And we have an angle here that I'm going to say is, I'm just going to call it alpha, just to call it something, but it's approximately that equal to what? It's approximately equal to this distance divided by r, because we have a right triangle whose hypotenuse is r, and whose opposite side is 2 delta x times 1 minus 1 over n. Well, 2 delta x times 1 minus 1 over n divided by r, we can bring the delta x and the r out here. That's a very straightforward rearrangement. And what's delta x over r? Delta x over r, notice I put the delta here, it wasn't there before, I missed it there as well. But the delta x over r is just the approximate angle theta sub I. So this just becomes 2 times 1 minus 1 over n theta sub I. Again, for n equals 1.33, this 2 times 1 minus 1 over n is going to be very close to 1/2. Okay, so this is going to be about half of this angle. So that, what do we have inside the triangle? Well, we have the angle that I labeled down here, theta I minus theta r. Here, we have a straight angle here. This obtuse angle is just equal to the straight angle minus theta sub I minus alpha. So I'm going to label this as pi minus theta sub I minus alpha. And that's this angle. But of course, theta sub I is delta x over r, and alpha is 2 times 1 minus 1 over n theta sub I. So we could write this out in more detail. Now this is in radians, so it's more convenient to work this, especially if we're doing the theoretical calculation in radians. Okay, so what's this angle going to be? This angle is going to be, well, the three angles of the triangle add up to pi. So it's going to be, let me get a different color here because this is kind of prominent. It's going to be pi minus this angle, that's theta I minus theta r, minus this angle, which is pi minus theta I minus alpha. Now the pi's go away. We have a minus theta I and a plus theta I, that goes away. But we do have an alpha here, okay? So, and we got the theta r. So it's going to be what? Theta r plus alpha. Now, alpha, of course, is 2 times 1 minus 1 over n times theta sub I, but that is the angle that we get. So I'm going to write out the result again. Keep the video from getting too long. Okay, when I got over to this point, I found that what I was getting made no sense. I had to go back and see what I'd done wrong. I carelessly took this angle to be this angle when I labeled the angle here. This angle is just theta sub r, so I'm going to have to make a couple of corrections. Okay, I think I've got the labeling straight. This is theta sub r up here. So theta sub I prime is what? It's pi minus theta sub r, because again, the three angles add up to 180 degrees. We're going to take the 180 degrees of the pi, subtract the theta sub r, subtract the pi minus theta sub I minus alpha, and what we're going to end up with the pi's subtract off, we're going to just end up with a theta sub I minus alpha, or minus theta sub r plus alpha. Now over here, alpha has been established as 2 times 1 minus 1 over n theta sub I. So theta sub I prime is alpha plus theta I minus theta r, 2 times 1 minus 1 over n theta I. And then we're going to add theta I. And then noting that theta r is theta I over n, we got theta I minus theta I over n. That's theta I times 1 minus 1 over n. When added to theta I times 2 times 1 minus 1 over n, we get 3 times 1 minus 1 over n theta sub I, if any of that makes any sense. Now this video is getting too long. I'm going to have to continue on a shorter video, show what happens if theta I is 14 degrees. It's going to follow that theta r is 10.5 degrees and theta I prime is coincidentally about 10.5 degrees. That's a coincidence of the fact that the n is about 1 1/3.